Humanity has always looked up at the stars with both awe and curiosity. We have set foot on the moon. We have sent robotic emissaries to every planet in our solar system. And we've even pushed machines like Voyager beyond the boundaries of our sun's influence into interstellar space. But a question lingers in the back of every dreamer's mind. Is interstellar travel truly possible? Could humans, or even machines, one day journey to another star and explore alien worlds circling suns light years away? It is a question that lies at the crossroads of science, engineering, and imagination. A question that tests the very limits of what it means to be human and whether our destiny is forever tied to our solar system or written across the stars. The immense scale of the universe. The universe is vast beyond human comprehension, and the distances between stars make interstellar travel one of the most daunting challenges we could ever attempt. Take Proxima Centauri, for instance, the closest star to our Sun beyond our solar system. It sits about 4.24 light-years away, which is roughly 40 trillion kilometers. To put that in perspective, Voyager 1, the fastest human-made object to leave our solar system, would take over 70,000 years to reach Proxima Centauri if it were headed in that direction. This gap isn't just a numerical inconvenience. It represents a fundamental obstacle. Even our own solar system, which seems immense to us, is minuscule on a galactic scale. The distance from the Sun to Neptune, the outermost planet, is only about 4.5 billion kilometers, a fraction of a single light-year. Compared to the 4 light-years to Proxima Centauri, even the entire stretch of our solar system is almost nothing. This highlights a sobering truth. When we talk about reaching other stars, we are not talking about a simple journey of months or years. We are discussing traversing distances that are millions to trillions of times greater than any human-made voyage so far. Moreover, these numbers are only the tip of the iceberg. Alpha Centauri, A and B, companions of Proxima Centauri in the same star system, are slightly farther away, and other nearby stars like Barnard's star are over 6 light-years distant. And that's just in our cosmic neighborhood. The Milky Way galaxy alone contains hundreds of billions of stars, spread across 100,000 light-years. Beyond that lies the even larger scale of the universe, with billions of galaxies, each with billions of stars. These numbers strain even the most vivid human imagination, illustrating that any journey to the stars isn't just a long trip, it's a leap across a gulf of space that dwarfs anything we have ever experienced. Understanding this scale is crucial because it frames every problem of interstellar travel, from propulsion to life support. Distances of this magnitude mean that conventional methods of space travel, which work for planets within our solar system, are almost laughably inadequate when applied to other stars. It is one thing to reach Mars in months, but quite another to cover 4.24 light-years with the technology we currently possess. Every concept of propulsion, energy, and human endurance must be rethought to make such a journey even conceivable. Current spacecraft speeds. To understand the challenge of interstellar travel, we first need to look at how fast our current spacecraft can travel, and then realize just how insufficient these speeds are for reaching even the nearest stars. Take Voyager 1, for example. Launched in 1977, Voyager 1 is currently the fastest human-made object relative to the Sun. It travels at roughly 61,000 kilometers per hour, which is about 17 kilometers per second. Impressive? Absolutely. But consider this. At that speed, it would take Voyager 1 over 70,000 years to reach Proxima Centauri. That's longer than recorded human history, longer than most civilizations have existed. It makes the challenge painfully clear. Our fastest spacecraft are still crawling in cosmic terms. Then there's the Parker Solar Probe, launched in 2018 with the mission of studying the Sun. Designed to get closer to the Sun than any previous spacecraft, it achieves speeds exceeding 700,000 kilometers per hour at its fastest, about 200 kilometers per second. That's a massive leap over Voyager. Yet even at that extraordinary velocity, it would still take over 6,600 years to travel the 4.24 light-years to Proxima Centauri. These numbers highlight an uncomfortable truth. Even our most advanced propulsion systems are painfully slow compared to the distances involved in interstellar travel. To put this into another perspective, consider that light, which travels at 300,000 kilometers per second, can cross the distance to Proxima Centauri in just over 4 years. Humans are nowhere near achieving even a fraction of that speed with current technology. To get close to interstellar timescales that would make the journey feasible within a human lifetime, spacecraft would need to travel at a significant percentage of the speed of light, a feat that current chemical rockets, ion engines, or solar-powered spacecraft cannot achieve. This comparison between what we have and what is required underscores the need for revolutionary propulsion technology. The velocities necessary for interstellar travel are orders of magnitude beyond our current capabilities, and bridging this gap will require breakthroughs not just in engineering, but in physics, energy storage, and material science. Until then, any journey to the stars remains a concept for the distant future. Time problem. One of the most striking challenges of interstellar travel is time itself. Even with our fastest spacecraft, reaching the nearest star would take tens of thousands of years. As mentioned earlier, Voyager 1, the fastest object humanity has ever built relative to the Sun, is moving at roughly 17 kilometers per second. At that speed, a journey to Proxima Centauri, a mere 4.24 light-years away, would require over 70,000 years. To put this into perspective, 70,000 years is longer than the entire span of human civilization as we know it, from the earliest hunter-gatherer societies to modern cities and technologies. A mission lasting that long is almost inconceivable in practical terms. Even if we were to consider the Parker Solar Probe, the fastest human-made object to date, capable of reaching speeds of up to 200 kilometers per second, the travel time to Proxima Centauri would still exceed 6,600 years. This is far beyond a human lifetime and challenges every notion of mission planning, life support, and even generational continuity. For any technology that relies on conventional propulsion methods, the time problem becomes the first insurmountable barrier. Humanity is accustomed to planning on scales of decades, maybe a century at most. Planning for thousands or tens of thousands of years is an entirely different level of temporal logistics, one that our societies are not equipped to manage. The implications of this are profound. A manned mission, for instance, is utterly impossible with current speeds. No single human could survive the journey, nor could our current technologies sustain life for millennia. Even unmanned robotic probes face challenges such as system degradation, cosmic radiation, and navigational precision over millennia. In essence, the sheer amount of time required with today's technology forces us to consider alternative approaches, faster propulsion methods, hibernation technologies, or entirely different paradigms of exploration. The time problem is not just a technical hurdle, it is a fundamental limit imposed by the vastness of space and the speed at which we can travel. Energy problem. One of the most formidable obstacles to interstellar travel is energy. Propelling a spacecraft to even a fraction of the speed of light requires an amount of energy that is almost inconceivable with today's technology. The kinetic energy needed for interstellar velocities grows exponentially as speeds increase. For example, accelerating a small spacecraft to just 10% of the speed of light would demand energy on the order of hundreds of terawatt-hours, more than the total electricity humanity consumes in a year. And that is for a relatively tiny probe. For a manned ship capable of carrying life support, radiation shielding, food, and other necessities, the energy demands would be astronomically higher. Conventional chemical rockets are hopelessly inadequate for this challenge. The energy density of chemical fuels is tiny compared to the requirements of interstellar travel. Even nuclear fission, which produces millions of times more energy per unit mass than chemical fuels, falls short for high-speed star-bound missions. Nuclear fusion, antimatter, and hypothetical exotic energy sources are considered as potential solutions precisely because they offer the energy densities necessary to reach relativistic speeds. Without such energy-dense propulsion methods, interstellar travel remains firmly in the realm of theoretical speculation. Furthermore, storing and safely managing such enormous energy presents additional engineering challenges. Energy sources powerful enough to push a spacecraft near light speed could generate extreme radiation, massive heat, and require materials that can withstand extraordinary stresses. Even small miscalculations in energy control at these scales could destroy the spacecraft outright. This is why energy is often considered the fundamental barrier to interstellar travel. Until humanity discovers a practical way to produce, store, and safely harness unfathomable quantities of energy, the dream of reaching another star remains far beyond our grasp. The physics of speed limits. When contemplating interstellar travel, one cannot ignore the ultimate speed limit imposed by the laws of physics, the speed of light. Albert Einstein's theory of special relativity, formulated in 1905, revolutionized our understanding of space, time, and motion, and it presents one of the most daunting barriers to humanity's starfaring ambitions. According to relativity, the speed of light in a vacuum is an unbreakable cosmic speed limit. Nothing with mass can reach, let alone exceed, this speed. The reasons for this limitation are both subtle and profound, rooted in the very structure of space-time and the relationship between energy and mass. At the heart of Einstein's theory is the famous equation, which tells us that mass and energy are interchangeable. As an object moves faster, it gains kinetic energy. However, relativity tells us that as the speed of an object approaches the speed of light, its effective relativistic mass increases. In other words, the faster you go, the heavier you become in a relativistic sense. As the speed gets closer to light speed, the mass increases asymptotically toward infinity. To continue accelerating the object, you need ever-increasing amounts of energy. Reaching the speed of light would require infinite energy, a physical impossibility with any conceivable technology. Even a tiny probe traveling at 90% of light speed requires energy on a scale far beyond humanity's current capacity, and that is without accounting for additional mass from life support systems, shielding, and propulsion infrastructure for a manned vessel. This mass-energy relationship has several cascading effects. First, it means that the faster you try to travel, the more fuel or energy you must carry to maintain acceleration. But fuel itself adds mass, which in turn requires more energy to accelerate, creating a vicious cycle of diminishing returns. Even the most optimistic fusion engines or antimatter propulsion systems would struggle to deliver enough energy to approach light speed for anything larger than a tiny, lightweight probe. This is one reason why many interstellar concepts focus on robotic missions or extremely light craft, such as the Breakthrough Starshot initiative, which envisions gram-scale probes pushed by powerful laser beams rather than massive starships. For humans, the energy required is orders of magnitude beyond our current or foreseeable engineering capabilities. Relativity also affects time in ways that can be both a curse and a boon for interstellar travel. According to time dilation, a phenomenon predicted by special relativity, time slows down for objects moving close to the speed of light relative to an outside observer. This means that for passengers on a relativistic spacecraft, a journey of several light years could take far less subjective time than it would for observers on Earth. While this seems like a potential advantage, humans might experience the journey as only decades rather than millennia. It doesn't reduce the actual energy requirements or solve the physical challenge of acceleration. Furthermore, from the perspective of Earth, the spacecraft would still take decades or centuries to arrive, making communication and synchronization with Earth nearly impossible over such vast distances. Another relativistic effect that complicates interstellar travel is the concept of length contraction. As a spacecraft approaches light speed, the distances along its direction of travel appear compressed from the perspective of the passengers. While this might make the journey feel shorter for travelers, it is a purely relativistic illusion. The universe does not shrink in reality. It only appears contracted from the moving frame of reference. From the standpoint of mission planning, engineering, and energy budgeting, the full spatial scale must still be accounted for. Navigation across multiple light years still involves contending with gravitational fields, interstellar dust, and potential collisions with micrometeoroids, all of which remain hazards regardless of relativistic effects. Even hypothetical propulsion concepts like the Alcubierre warp drive, which seeks to circumvent relativity by contracting space in front of a ship and expanding it behind, rely on the existence of exotic matter with negative energy density, something that has never been observed or produced in usable quantities. While such ideas tantalize the imagination, they do not negate Einstein's fundamental limit. Moving through normal space faster than light still appears impossible. Any practical interstellar vehicle must respect relativistic constraints or rely on mechanisms that manipulate space-time itself, rather than conventional acceleration. The physics of speed limits also dictates the design of future interstellar missions. Even if propulsion technology advances dramatically, engineers must plan for extremely long travel times, relativistic radiation exposure, and the fact that acceleration and deceleration require immense energy. These constraints have led to concepts like generational ships, where humans live and die over centuries-long voyages, and robotic probes, which can survive longer durations and tolerate harsh conditions. High-speed interstellar travel is not simply a question of building a faster rocket. It is a question of fundamentally rethinking how humanity interacts with the cosmos under the unyielding rules of physics. Relativity also has implications for interstellar navigation. At relativistic speeds, collisions with even tiny particles of dust or gas in interstellar space can release tremendous amounts of energy, equivalent to high-speed bullets. These collisions could easily destroy a spacecraft moving near light speed. Protective shielding could mitigate some of the risks, but the added mass would further increase energy requirements, reinforcing the vicious cycle imposed by relativistic mass increase. Every incremental increase in velocity becomes exponentially more challenging, and the technical hurdles compound at near light speeds. Ultimately, Einstein's speed limit defines a clear boundary for what is achievable with our current understanding of physics. While it does not entirely rule out interstellar travel, it imposes fundamental constraints that make near light speed travel extraordinarily difficult. Any realistic interstellar mission must either accept prolonged travel times, measured in centuries or millennia, or explore entirely new paradigms of propulsion, energy generation, and material science. The laws of physics, as we understand them, make humanity's dreams of zooming to the nearest star in a human lifetime an immense technological challenge, but they also provide a framework that guides our engineering, imagination, and exploration. By respecting these limits, we can begin to chart plausible paths to the stars, even if those paths are measured in lifetimes rather than years. Generational ships. Given the immense distances and the insurmountable energy demands posed by near light speed travel, one of the most compelling concepts for human interstellar exploration is the generational ship. These enormous spacecraft are designed not to reach another star within a single human lifetime, but to sustain multiple generations of humans over the course of centuries or even millennia. The idea is both pragmatic and visionary. If no single person can survive the journey to Proxima Centauri or beyond, then the journey must become a self-contained society, a moving microcosm of Earth itself, continuously sustaining and evolving as it slowly traverses the cosmos. Generational ships present a host of engineering, biological, and social challenges. First, there is the question of size and infrastructure. To support a self-sustaining population, A generational ship must contain not only living quarters, but also agricultural systems capable of producing food, oxygen, and water indefinitely. Closed-loop ecosystems would need to recycle waste and maintain balance, essentially recreating a miniature biosphere inside a spacecraft. Advanced hydroponics, aquaponics, and possibly synthetic biology could play crucial roles, but even the most sophisticated systems would need to operate flawlessly for centuries. A single failure could cascade into catastrophic consequences for the entire ship, threatening thousands of lives. The psychological and social dimensions of life aboard a generational ship are equally daunting. Imagine living your entire life aboard a spacecraft, knowing that your ancestors began the journey long before you and your descendants may never see Earth again. Cultural continuity would be vital. Education, governance, and social structures would need to be designed to preserve knowledge, prevent societal collapse, and ensure cooperation over hundreds of years. Conflict management, mental health, and population control would all become central concerns. Would people born aboard the ship accept their place in a multi-generational mission? Or would rebellion and dissent threaten the project's stability? Sociologists and psychologists would need to design a culture capable of surviving the pressures of isolation, monotony, and a confined environment for centuries. Technologically, a generational ship would have to solve the problem of propulsion in a way that balances energy efficiency, sustainability, and safety. Chemical rockets are completely inadequate. Even nuclear propulsion might struggle over such long durations, unless the systems are incredibly reliable and capable of continuous operation. Solar sails or laser-driven propulsion could be used for the initial acceleration phase, but the ship would likely need a method of long-term, low-thrust propulsion for course adjustments over centuries. Redundancy and repair capabilities would be critical. Any component failure must be fixable by the ship's inhabitants, many of whom may not be engineers by training, over generations of accumulated expertise. Life aboard a generational ship would also require addressing human biology in ways we rarely consider today. Cosmic radiation poses a constant threat over long interstellar distances, especially outside protective planetary magnetic fields. Shielding the ship from high-energy particles might involve a combination of thick hull materials, magnetic fields, or even utilizing water and other consumables as protective barriers. Medical technology would need to be advanced enough to handle disease, injury, and aging without access to Earth-based hospitals. The generational ship concept has been explored extensively in science fiction, from novels like Orphans of the Sky to Rendezvous with Rama, but it also attracts serious scientific consideration. Projects like the NASA 100-Year Starship Initiative have examined the feasibility of multi-generational travel, looking at propulsion, sustainability, and human factors as part of long-term research. These ships would essentially function as small, self-contained civilizations in space, raising profound questions about identity, ethics, and the nature of human life when detached from a home planet. Despite the immense challenges, generational ships represent a practical approach to interstellar travel given current and near-future technology. While we may not yet have the propulsion methods to reach the nearest star in a few decades, creating a self-sustaining community capable of enduring a journey of hundreds of years is at least conceptually within the realm of possibility. It forces humanity to think not just about engineering and physics, but about how to preserve society, culture, and life itself over timescales far beyond the typical human experience. These ships are, in a sense, humanity's insurance policy against cosmic isolation, a means of spreading life to the stars while remaining tethered to the continuity of our species. Generational ships also raise philosophical and ethical questions. If multiple generations live and die aboard a spacecraft without ever seeing the destination, what moral obligations do we have to those future inhabitants? How do we ensure that each generation retains the skills, knowledge, and motivation to continue the mission faithfully? Furthermore, Would a society entirely confined to a spacecraft evolve in ways we cannot predict, perhaps developing its own culture, priorities, and values that diverge from Earth? These questions underscore the reality that interstellar travel is not just a technological challenge. It is a social, biological, and ethical experiment played out on a cosmic scale. Ultimately, generational ships highlight the tension between human ambition and the limitations imposed by physics and distance. They offer a vision of interstellar exploration that is slow, deliberate, and deeply human, emphasizing endurance, adaptability, and societal resilience over speed and immediacy. While we may dream of zooming to the nearest star in a lifetime, generational ships remind us that the journey itself may define the adventure as much as the destination. Cryogenic sleep, another concept often proposed to overcome the enormous time barriers of interstellar travel, is cryogenic sleep, or suspended animation. Unlike generational ships, which rely on entire communities living and evolving over centuries, cryogenic sleep envisions putting humans into a state of near-complete stasis. In theory, travelers could remain frozen or biologically slowed throughout the journey, essentially pausing their life processes until the destination is reached. This idea is particularly appealing because it promises to preserve individual lifespans while avoiding the enormous logistical and societal complexities inherent in multi-generational voyages. Cryogenic sleep is not purely science fiction. Humans have experimented with induced hypothermia and torpor in medical contexts. For instance, lowering a patient's body temperature can slow metabolism and reduce oxygen requirements, giving doctors more time to perform life-saving procedures. Some animals naturally enter states of hibernation, drastically reducing their metabolic rates for months without ill effects. Drawing inspiration from these biological examples, researchers have theorized that it might be possible to safely induce humans into a long-term state of suspended animation. The potential benefit for interstellar travel is obvious. If travelers can remain in stasis for decades, centuries, or even longer, the enormous distances between stars suddenly become more manageable. However, the technical challenges of long-term cryogenic sleep are monumental. First, the human body is exquisitely sensitive to temperature, oxygen levels, and biochemical balance. Simply freezing a human solid would cause catastrophic cellular damage. Ice crystals would rupture cell membranes, destroying tissues irreversibly. To circumvent this, researchers consider techniques such as vitrification, where the body is cooled and preserved without forming ice crystals. Even with vitrification, maintaining organ function and avoiding biochemical breakdown over long durations remains an unsolved problem. Currently, cryogenic preservation is used experimentally in organ banking for short-term storage, but extending this to entire humans for decades or centuries is beyond current capability. Long-term stasis also raises medical and biological questions that are not fully understood. How do we prevent the accumulation of DNA damage over extended periods? How do we address muscle atrophy, bone density loss, and organ degradation that naturally occur when metabolism is halted or slowed? Even if freezing were possible, the process of reanimation presents additional hurdles. The technology would need to reliably restore complex cellular and neurological function without introducing severe side effects, ensuring that humans awaken fully capable of surviving in a distant star system. There is also the question of aging. If the suspension is truly metabolic stasis, travelers might arrive without aging at all, but any incomplete stasis or metabolic activity over the journey could accelerate deterioration or unpredictably alter physiological systems. Psychological and ethical dimensions cannot be ignored either. Travelers would effectively be committing themselves to a journey whose length they could not experience consciously. They would trust entirely in the reliability of technology and subsequent generations of engineers or AI monitoring the spacecraft. The uncertainty surrounding successful reanimation introduces ethical dilemmas. Should humans be subjected to a technology with such enormous risks? Who would decide which individuals are chosen for interstellar sleep, and how would they consent to a voyage that spans lifetimes beyond their conscious control? Moreover, if something goes wrong during the voyage, if power systems fail, if cryogenic systems malfunction, or if unforeseen environmental hazards strike, the travelers might never wake. Despite these challenges, cryogenic sleep remains one of the most attractive solutions for single-generation interstellar travel. Unlike generational ships, it avoids the need for a self-sustaining society aboard a spacecraft, drastically reducing the mass, complexity, and life support requirements of the vessel. It also has the potential to dramatically reduce mission costs, as fewer resources would be needed to support a sleeping crew than an entire living population over centuries. In theory, combining cryogenic sleep with advanced propulsion systems such as fusion engines, light sails, or even laser-driven acceleration could allow humans to reach the nearest star systems within a time frame compatible with a single human lifespan. The appeal of cryogenic sleep lies not only in its practical potential, but also in its poetic quality. The notion of humans pausing their lives, drifting silently through the void between stars, only to awaken in an alien system, embodies the ultimate adventure of interstellar exploration. It offers a vision of humanity that bridges the gap between the limits of our biology and the vast distances of the cosmos. While the technology remains speculative and fraught with unsolved problems, research into hibernation, metabolic suppression, and cryopreservation continues to advance. Each incremental breakthrough brings the dream of sleeping through centuries-long voyages closer to reality. Cryogenic sleep represents a middle path between the extremes of slow, multi-generational travel and the impossibility of near light-speed propulsion. It offers hope that humans might one day traverse the enormous gulf between stars without requiring centuries of continuous societal cohesion or the unimaginable energy demands of relativistic travel. While the challenges are immense, biological, technical, and ethical, the concept forces us to reconsider what it means to survive, endure, and explore in a universe defined by vast scales and unforgiving physics. Robotic probes. Given the overwhelming challenges of human interstellar travel, time scales spanning centuries, energy requirements beyond current capabilities, and the immense complexity of life support systems, robotic probes and AI-driven spacecraft emerge as the most realistic candidates for humanity's first ventures beyond our solar system. These machines do not require food, water, or oxygen, are impervious to psychological stress, and can survive in environments that would be lethal to humans. In many ways, robotic probes represent the practical bridge to the stars, allowing exploration of other star systems long before humans could physically arrive. Historically, robotic probes have already demonstrated the extraordinary capabilities of unmanned exploration. The Voyager spacecraft, launched in the 1970s, continued to send data from interstellar space decades after their departure. Cassini orbited Saturn for over a decade, sending back thousands of images and measurements of Saturn and its moons. The success of these missions illustrates a key advantage of robotic explorers: longevity. While humans are constrained by lifespans, robots can endure, repair, and adapt to harsh environments for decades, centuries, or potentially millennia if autonomous systems are robust and self-repairing. AI further enhances the feasibility of robotic interstellar missions. Unlike early spacecraft that relied entirely on Earth-based instructions, future probes could be equipped with advanced artificial intelligence capable of autonomous decision-making. This autonomy would be crucial for interstellar distances, where communication delays of years or even decades make real-time guidance from Earth impossible. AI systems could handle navigation, system repairs, scientific data collection, and adaptive problem-solving. For example, if a micrometeoroid were to damage a critical component, an AI could immediately implement repairs or reroute functions, preserving the mission without waiting for Earth's intervention. The Breakthrough Starshot initiative exemplifies how robotic probes could lead the way in interstellar exploration. This project envisions sending thousands of gram-scale star chips equipped with cameras and sensors to Alpha Centauri, propelled by powerful ground-based lasers that push ultralight sails to speeds approaching 20% of the speed of light. While these probes are tiny compared to human-rated spacecraft, their high velocity would allow them to reach the nearest stars in decades rather than millennia. The Starshot concept demonstrates a practical strategy. Instead of risking human lives or attempting to accelerate massive spacecraft, small, intelligent robotic explorers can traverse interstellar distances far faster and more feasibly. Robotic probes also eliminate the logistical nightmare of life support, shielding against cosmic radiation for humans, or food and water storage. Radiation is a significant hazard in interstellar space, capable of damaging both electronics and biological systems. While humans require thick shielding that adds massive weight and energy costs, robotic systems can employ hardened electronics, error-correcting software, and redundancy to survive the same environment with far less mass and complexity. In other words, robots make interstellar travel achievable in a way that humans currently cannot, not by bypassing the laws of physics, but by designing missions suited to the harsh realities of space. Another advantage of robotic probes is scalability. Sending multiple probes to a star system increases the likelihood of success. Even if some fail en route due to collisions with interstellar particles or equipment failure, others may survive and return valuable data. This swarm approach also allows parallel exploration of different targets or collection of varied data sets, something impossible with a single human crew. By deploying fleets of intelligent probes, humanity can explore distant systems in a cost-effective, low-risk manner, laying the groundwork for eventual human travel or colonization once technology advances sufficiently. Despite these advantages, robotic probes face challenges of their own. Communication over interstellar distances is slow and limited, meaning probes must operate largely independently. Power generation for decades-long missions is another obstacle. Solar panels become ineffective far from stars, necessitating long-lived nuclear batteries or other energy sources. Miniaturization of instruments must balance size, durability, and scientific capability. AI systems must be sophisticated enough to handle unanticipated problems, but robust enough to avoid catastrophic errors. Philosophically, robotic probes raise intriguing questions about the role of humans in space exploration. If AI-driven machines reach other star systems first, will humanity ever experience those worlds directly? Or will we rely entirely on the data and images transmitted across light years of distance? This scenario challenges traditional notions of exploration and discovery, emphasizing observation and knowledge over physical presence. Yet it also provides a pragmatic path forward. While humans remain bound to the solar system, our robotic emissaries could carry our curiosity and ingenuity to the stars, effectively extending humanity's reach without the prohibitive costs and risks of manned interstellar travel. Robotic probes and AI represent the most viable method for humanity's first forays into interstellar space. They circumvent the immense challenges of time, energy, life support, and human vulnerability, allowing us to begin exploring neighboring stars within the foreseeable future. By sending machines first, we gain knowledge, refine technology, and prepare for the day when humans might eventually follow. In many ways, robots will be our pathfinders, our ambassadors to the stars, and our means of turning what currently seems impossible into a tangible reality. Solar sails. Among the most intriguing and potentially practical methods for achieving interstellar travel are solar sails, also called light sails. The concept is elegantly simple yet profoundly ambitious. A large, ultra-thin reflective surface captures the momentum of photons, either from sunlight or from directed lasers, to gradually accelerate a spacecraft. Unlike conventional rockets, which rely on chemical propellants that are heavy and finite, solar sails use the momentum of light, which is effectively limitless, as a propulsion source. Over long distances, this constant but gentle push can achieve velocities far higher than what chemical rockets can provide, potentially bringing interstellar travel within reach. The physics behind solar sails is based on radiation pressure. Photons, though massless, carry momentum, and when they strike a reflective surface, that momentum is transferred to the sail, producing a tiny thrust. Individually, each photon contributes an infinitesimal amount of force, but a large enough sail exposed to continuous light over vast distances can generate measurable acceleration. The effect is cumulative. Unlike traditional propulsion, which expends fuel in a relatively short burst, a solar sail continues to accelerate as long as it is exposed to light, potentially reaching speeds that are a significant fraction of the speed of light over years or decades. One of the most ambitious real-world initiatives leveraging this concept is the Breakthrough Starshot project. Announced in 2016, the initiative proposes sending thousands of tiny, gram-scale probes to the Alpha Centauri system using light sails propelled by high-powered, ground-based lasers. These starships would ride sails only a few meters wide, but incredibly light and reflective, allowing the probes to accelerate to up to 20% of the speed of light. At such velocities, a journey to Proxima Centauri could be completed in approximately 20 years, a time frame that is humanly conceivable, unlike the millennia required by conventional spacecraft. The Starshot approach highlights a key advantage of light sails. They allow very high-speed travel without carrying massive fuel loads, drastically reducing the spacecraft's mass and energy constraints. The concept of solar sails is not purely theoretical. Several missions have successfully tested the principle within our solar system. Japan's Icaros mission, launched in 2010, demonstrated solar sail propulsion in space, using a large, thin sail to slowly accelerate away from the Sun. LightSail, a project funded by the Planetary Society, similarly demonstrated solar sail deployment and propulsion in Earth orbit. These early missions validate the fundamental mechanics of light-driven acceleration and pave the way for more ambitious interstellar applications. While the promise of solar sails is immense, the technology faces several significant challenges. For one, constructing sails that are simultaneously lightweight, reflective, and strong enough to withstand interstellar conditions is extremely difficult. The sails must endure micrometeoroid impacts, cosmic radiation, and the extreme cold of deep space without tearing or losing their reflective properties. Additionally, maintaining the correct orientation to maximize thrust and navigate accurately over light years of travel requires advanced guidance systems and autonomous control, as real-time corrections from Earth would be impossible due to light-speed communication delays. Laser propulsion, as envisioned in Breakthrough Starshot, adds another layer of complexity. The project would require an enormous ground-based laser array capable of delivering concentrated beams across thousands of kilometers to push the sail to relativistic speeds. The engineering challenges here are monumental. The lasers must remain precisely aligned over long distances, and the energy requirements are staggering, potentially exceeding the output of entire power grids. Furthermore, as the sail accelerates, the spacecraft must remain stable and intact, enduring enormous accelerative forces that could rip apart weaker materials. Despite these obstacles, solar sails offer a pathway to interstellar exploration that bypasses many of the limitations of conventional propulsion. They eliminate the need for carrying massive amounts of fuel, avoid many of the life support and energy issues associated with human crews, and could, in principle, reach velocities approaching a significant fraction of light speed. In addition, solar sails can be scaled. Smaller, lighter probes can be launched en masse, increasing the probability that at least some will survive the long voyage to nearby star systems. This swarm approach mirrors strategies used in robotic probes, but with the advantage of high-speed propulsion over interstellar distances. Solar sails also raise philosophical and strategic questions about exploration. They represent a mode of travel that is slow to start, but relentless in progress, relying on the constant push of light over time. Unlike chemical rockets that provide immediate thrust but quickly exhaust fuel, light sails embody patience, persistence, and cumulative motion, a metaphorical as well as practical approach to crossing the vast emptiness between stars. By exploiting the natural forces of the universe, humanity can send its emissaries into the cosmos in a way that respects the laws of physics while circumventing many of the limitations imposed on conventional propulsion methods. In summary, solar sails and laser-driven light propulsion offer one of the most plausible near-future methods for interstellar travel, particularly for robotic or miniature probes. By using photons rather than fuel, these technologies promise a route to velocities far beyond current spacecraft, potentially reaching nearby stars within a human lifetime. While massive engineering, material, and energy challenges remain, the concept transforms interstellar travel from a distant dream into a tangible, though still highly ambitious, possibility. In the realm of propulsion, solar sails stand out as a symbol of ingenuity, offering humanity a practical way to ride the momentum of light itself to the stars. Fusion. Propulsion. Nuclear fusion, the same process that powers the Sun, has long been considered one of the most promising avenues for high-speed interstellar travel. Unlike chemical rockets, which are severely limited by the energy stored in conventional fuels, fusion releases enormous amounts of energy per unit mass by combining light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, into heavier elements. The resulting reaction produces both energy and high-velocity particles, which can be harnessed for thrust. Fusion propulsion, in theory, offers the combination of high thrust and extremely high efficiency required to make journeys to the nearest stars conceivable within decades rather than millennia. One proposed approach is the fusion rocket, which would generate thrust by expelling the high-energy plasma created from fusion reactions at enormous speeds. Unlike chemical rockets, which achieve exhaust velocities of just a few kilometers per second, fusion rockets could, in theory, reach tens of thousands of kilometers per second, approaching a significant fraction of light speed. This increase in exhaust velocity dramatically reduces travel times, bringing interstellar missions into the realm of human lifespans. For example, a fusion-powered probe could potentially reach Alpha Centauri in 50 to 100 years, a time frame that, while still long, is feasible for a single generation and far faster than the thousands of years required with current technology. Several fusion propulsion concepts have been proposed over the decades. One is the Daedalus project, conceived in the 1970s by the British Interplanetary Society. Daedalus was envisioned as a massive, unmanned starship propelled by pellets of deuterium and helium-3, ignited in a fusion reaction chamber. This pulsed fusion approach would release tremendous amounts of energy, pushing the spacecraft to up to 12% of the speed of light. While purely theoretical, the Daedalus concept demonstrated that fusion propulsion is at least physically plausible within the bounds of known science, provided sufficient energy and materials can be obtained. Helium-3, in particular, is rare on Earth, but may be harvested from gas giants like Jupiter, highlighting both the potential and the logistical challenges of implementing such a system. A more modern variation of fusion propulsion involves inertial confinement fusion, where tiny fuel pellets are bombarded by lasers or magnetic fields to induce a controlled fusion reaction. This technique, already used experimentally in fusion energy research on Earth, could, in theory, provide a series of mini-explosions to propel a spacecraft steadily through space. Magnetized target fusion, another concept, combines features of magnetic confinement and inertial confinement to achieve stable, repeatable fusion pulses. Each of these approaches faces enormous technical hurdles, from containing plasma at millions of degrees to developing materials that can withstand repeated fusion pulses without failure. The advantages of fusion propulsion extend beyond speed. Fusion fuel is relatively abundant compared to antimatter or exotic energy sources, and the energy density of fusion is orders of magnitude higher than chemical reactions. This efficiency allows spacecraft to carry less fuel relative to their mass, reducing launch costs and structural complexity. Moreover, fusion propulsion can be designed for long-duration thrust, meaning a spacecraft could accelerate continuously for years, gradually approaching a high fraction of the speed of light. This long-term, steady acceleration could also help mitigate some of the time dilation effects predicted by relativity, allowing human passengers or sensitive instruments to experience a shorter subjective journey while still respecting the universal speed limit. Despite its promise, the practical realization of fusion propulsion faces staggering challenges. Controlled nuclear fusion has eluded sustainable, net positive energy production on Earth for decades, though research continues aggressively with projects like ITER and various private sector initiatives. Scaling these principles to a spacecraft capable of operating autonomously in the harsh environment of space compounds the difficulty. Heat management, radiation shielding, and precision engineering of the fusion chamber are just a few of the critical issues that must be solved. Even if technical obstacles are overcome, building a fusion-powered starship would require enormous resources, cutting-edge materials, and decades of research and development. Fusion propulsion also raises operational and ethical considerations for crewed interstellar travel. Continuous acceleration over years or decades could subject passengers to prolonged periods of artificial gravity or high G-forces, depending on the ship's design. Shielding from the intense radiation generated by the fusion reactions would be critical to avoid long-term health effects. Life support systems, food production, and psychological well-being for a long-duration mission would need to be integrated seamlessly with the propulsion system. This makes a fusion-powered generational ship or a cryogenic mission a complex synthesis of multiple cutting-edge technologies rather than a single solution. In conclusion, nuclear fusion offers perhaps the most scientifically realistic path toward high-speed interstellar travel. Unlike concepts that rely on speculative physics or exotic matter, fusion propulsion is grounded in well-understood principles of energy release and momentum. While significant engineering, financial, and material challenges remain, a fusion-powered spacecraft could dramatically reduce travel times to nearby stars, making human exploration, or at least robotic exploration on unprecedented scales, a conceivable goal for the next century. Fusion propulsion bridges the gap between current chemical rockets, which are hopelessly slow, and the dream of relativistic travel, positioning it as one of the most promising avenues in the quest to extend humanity beyond the solar system. Antimatter engines. Antimatter propulsion represents one of the most powerful and theoretically efficient methods for interstellar travel, but it is also one of the most speculative. Antimatter is composed of particles that are the mirror opposite of normal matter, positrons, anti-electrons, or antiprotons, for example. When antimatter comes into contact with regular matter, the two annihilate each other in a burst of energy, converting their mass almost entirely into pure energy according to Einstein's equation. The energy density of antimatter is staggering. 1 gram of antimatter reacting with 1 gram of matter releases roughly the same energy as the detonation of a nuclear bomb, making it millions of times more powerful than chemical fuels and thousands of times more efficient than nuclear fusion. In theory, antimatter engines could accelerate spacecraft to a significant fraction of the speed of light, making interstellar travel feasible within a human lifetime. The appeal of antimatter propulsion lies in its energy efficiency. Because antimatter converts nearly all of its mass into usable energy, it would allow spacecraft to reach relativistic speeds with far less fuel mass than chemical or even fusion-based engines. A relatively small quantity of antimatter could, in theory, propel a spacecraft large enough to carry humans or complex scientific instruments to nearby stars. For instance, an antimatter-powered probe could potentially reach Alpha Centauri in decades rather than centuries, depending on the fraction of light speed achieved and the efficiency of the propulsion system. This makes antimatter one of the few methods capable of bridging the enormous distances of interstellar space within timeframes compatible with human lifespans. However, producing antimatter is currently one of the most difficult and expensive processes in physics. Antimatter is not naturally abundant on Earth, and it must be manufactured in particle accelerators at extraordinary energy cost. For example, creating just a milligram of antimatter could require the energy output of a major city for an entire year, making large-scale production impractical with current technology. Moreover, antimatter cannot be stored in conventional containers, as any contact with regular matter would result in immediate annihilation. Magnetic confinement and vacuum traps are currently used to store tiny quantities for experimental purposes, but scaling these systems to hold kilograms or more, enough to power a starship, is far beyond our current engineering capabilities. Even if production and storage hurdles could be overcome, antimatter engines pose significant safety concerns. A leak, accident, or containment failure could release massive amounts of energy instantaneously, effectively destroying the spacecraft and anything nearby. Shielding both the crew and sensitive electronics from the gamma rays and high-energy particles generated during antimatter reactions is another challenge. Any practical antimatter propulsion system would require highly sophisticated containment fields, redundant safety mechanisms, and precise control over the reaction rate to convert the annihilation energy into usable thrust efficiently. Various theoretical designs for antimatter engines have been proposed. One is the direct annihilation drive, where antimatter reacts with matter in a controlled chamber, ejecting the resulting high-energy particles as propellant to generate thrust. Another is the annihilation-powered photon drive, which converts the energy entirely into directed gamma rays or high-energy photons, essentially creating a photon rocket. Photon rockets could theoretically approach the speed of light, though they would require perfect efficiency in energy conversion and advanced shielding to protect the spacecraft. A third design is hybrid antimatter fusion propulsion, where antimatter is used to catalyze fusion reactions, combining the advantages of both high energy density and relatively manageable containment requirements. Despite the immense theoretical power of antimatter engines, the technical, financial, and safety challenges remain almost insurmountable at present. Generating the required quantities of antimatter would consume more energy than we currently produce globally, and the containment technology needed to store it safely for long-duration missions does not exist. Additionally, the engineering required to convert annihilation energy into directed thrust efficiently and reliably is orders of magnitude beyond current propulsion systems. This makes antimatter engines an exciting but distant prospect, one that may remain in the realm of theoretical studies and science fiction for decades or even centuries. Philosophically, antimatter propulsion challenges humanity to consider the limits of technology versus the boundaries of physics. It represents a pathway to relativistic interstellar travel, potentially shrinking the vast distances between stars to manageable timescales, but it also underscores the enormous gap between theoretical physics and practical engineering. While antimatter engines could, in principle, make near-light speed travel possible, they force us to confront issues of resource scarcity, safety, and the extreme difficulty of scaling laboratory experiments to interstellar-scale missions. In summary, antimatter engines epitomize the dream of high-speed interstellar travel, nearly unparalleled energy density, and the potential to reach relativistic velocities. Yet, the enormous challenges of production, storage, containment, and energy conversion make this concept highly speculative. For now, antimatter propulsion serves as a tantalizing possibility that inspires scientists and engineers. a reminder of the incredible energy hidden in the universe and the extraordinary ingenuity required to harness it. If ever realized, antimatter engines could transform interstellar exploration, turning what currently seems impossible into a daring, high-speed reality. Wormholes. Wormholes, sometimes called Einstein-Rosen bridges, represent one of the most fascinating and speculative ideas for interstellar travel, offering the tantalizing possibility of bypassing the vast distances between stars entirely. In theory, a wormhole is a tunnel-like structure connecting two distant points in space-time, allowing instantaneous or near-instantaneous travel between them. If such structures exist and could be stabilized, they could reduce a journey of light years to a matter of minutes or hours, fundamentally rewriting our understanding of space, time, and the limits of travel. Wormholes are rooted in the equations of general relativity, which allow solutions in which space-time can be bent and connected in unusual ways. The concept was first formalized in the 1930s by Albert Einstein and Nathan Rosen, who proposed that such bridges could mathematically exist as a consequence of their relativistic equations. In these solutions, a throat connects two regions of space-time, potentially linking distant stars, galaxies, or even different universes. The idea gained traction in theoretical physics because it does not outright violate known physical laws, though it introduces conditions and constraints that challenge our understanding of matter, energy, and causality. Wormholes remain purely theoretical. No observational evidence suggests that naturally occurring wormholes exist, and constructing one artificially would require manipulating space-time in ways far beyond our current capabilities. One of the central challenges of wormholes is stability. Even if a wormhole could be created, it would likely collapse almost instantaneously unless exotic matter with negative energy density were used to hold it open. This negative energy would counteract the natural tendency of the wormhole to pinch off, but exotic matter is hypothetical and has only been observed in extremely limited, small-scale quantum experiments. The quantities required to stabilize a macroscopic wormhole capable of transmitting humans or spacecraft would be astronomical, far beyond anything achievable with foreseeable technology. Without such matter, any attempt to enter a wormhole could result in catastrophic collapse, crushing or vaporizing anything inside. Traversable wormholes also pose extreme relativistic and quantum challenges. Even if stabilized, passing through a wormhole might involve exposure to intense tidal forces, gravitational gradients, or unknown quantum phenomena that could destroy matter or information. The energy required to create or enlarge a wormhole to human-scale dimensions would likely exceed the total energy output of entire stars. Moreover, the very existence of a stable wormhole capable of instantaneous travel could potentially violate causality, leading to paradoxes such as backward time travel, which challenge the foundations of physics as we understand it. Some theoretical models suggest that the laws of quantum mechanics or general relativity themselves might forbid the formation of macroscopic, traversable wormholes, making them a tantalizing but potentially unreachable dream. Despite these obstacles, wormholes remain a popular subject of both scientific inquiry and science fiction, because they offer a method of interstellar travel that circumvents the immense time, energy, and distance problems associated with conventional propulsion. If feasible, a wormhole would allow a spacecraft to effectively teleport between star systems, bypassing centuries-long journeys and the relativistic limits imposed by light-speed travel. This would render concepts like generational ships, cryogenic sleep, or fusion propulsion largely unnecessary for human explorers, as the stars could be reached almost instantaneously. Theoretical physicists have also explored smaller-scale manifestations of wormholes. Quantum fluctuations may create transient microscopic wormholes, sometimes called quantum foam, at scales far smaller than atoms. While these mini wormholes are too tiny to transmit matter, They suggest that space-time itself is more flexible and dynamic than it appears. Understanding the properties of such structures could eventually inform the possibility of larger, stabilized wormholes, though this remains speculative. Research into quantum gravity, string theory, and other advanced areas of physics may one day provide insights into whether macroscopic wormholes are physically realizable. Beyond the physics, wormholes raise profound philosophical and practical questions. Even if a stable wormhole could be created, how would we know where it leads? Could it connect to the right star system, or even the right location within a system? What safeguards would be necessary to prevent catastrophic miscalculations? Furthermore, ethical considerations would arise if humans were to use a technology capable of bending space-time itself, potentially with consequences for causality, time, and the fabric of the universe. The very act of traversing a wormhole could involve unknown risks that no current experiment can predict. In essence, wormholes occupy the boundary between rigorous theoretical physics and imaginative speculation. They offer a vision of interstellar travel that is orders of magnitude faster than any conventional method, but they remain entirely hypothetical, limited by our incomplete understanding of space-time, energy, and quantum phenomena. While they captivate the imagination, the practical obstacles, stabilization, exotic matter, safety, and energy, are immense, making wormholes an unlikely solution for near-term human interstellar exploration. Yet, the concept serves as a powerful reminder of the potential flexibility of the universe and the extraordinary ingenuity that may be required to travel among the stars. Warp drives. The concept of warp drives, particularly the Alcubierre drive, represents one of the most audacious ideas for interstellar travel, allowing theoretical speeds far beyond what conventional propulsion could achieve. Unlike traditional spacecraft, which must accelerate through space, a warp drive would manipulate space-time itself. Proposed in 1994 by Mexican physicist Miguel Alcubierre, the Alcubierre drive envisions compressing space-time in front of a spacecraft while expanding it behind. The spacecraft itself would reside within a warp bubble, a region of flat space-time, effectively moving faster than light relative to the external universe, without violating Einstein's special relativity locally. Within this bubble, the ship never actually moves faster than light in its immediate surroundings, circumventing the usual relativistic speed limits. The appeal of the Alcubierre drive lies in its potential to make interstellar travel dramatically faster. In theory, a warp bubble could allow a spacecraft to cross the 4.24 light-years to Proxima Centauri in a matter of days or weeks, rather than decades or centuries. This would revolutionize the concept of space exploration, transforming journeys that would otherwise span human lifetimes into trips achievable within a single generation. The drive essentially separates the motion of the spacecraft from the motion of space-time itself, using the universe's fabric as a conveyor belt to bridge immense distances almost instantaneously. This is why warp drives capture both scientific and popular imagination. They suggest a practical solution to the otherwise insurmountable barrier of light-speed travel. However, translating the Alcubierre concept into reality faces enormous theoretical and engineering challenges. The most significant requirement is exotic matter with negative energy density, a substance that does not naturally exist in quantities anywhere near those needed. Negative energy is theoretically possible in the quantum world, as demonstrated in the Casimir effect, where certain configurations of electromagnetic fields create regions of negative energy density. Yet scaling such effects to produce a stable, macroscopic warp bubble capable of moving a starship is far beyond current experimental capability. The quantity of exotic matter needed for even a small spacecraft has been estimated to be comparable to or greater than the mass of Jupiter, though later refinements of the Alcubierre metric suggest that more efficient configurations could reduce the required energy significantly. Still, the energy requirements remain astronomical. Another major challenge is stability and control. A warp bubble if achievable, would involve intense curvature of space-time, potentially creating extreme tidal forces, gravitational gradients, and other relativistic effects. Controlling the bubble's shape and maintaining a stable passage through space would demand unprecedented precision and a profound understanding of gravitational physics. If the bubble were misaligned or destabilized, the consequences could range from the spacecraft being torn apart to catastrophic effects on nearby regions of space. Moreover, recent theoretical analyses suggest that a warp bubble might generate enormous amounts of high-energy radiation at its edges, potentially harming the spacecraft and anything in its path once the bubble collapses or decelerates. Shielding against this radiation presents yet another daunting engineering obstacle. The concept also raises questions about causality and the nature of time. Moving faster than light relative to external observers implies potential violations of causality, theoretically allowing scenarios akin to backward time travel or closed time-like curves. While the Alcubierre drive is designed to avoid local violations of special relativity, its global effects on spacetime could be far more complex, raising theoretical concerns about paradoxes and the consistency of physics. Quantum effects, unknown instabilities, or limitations imposed by the fabric of spacetime itself might prevent the creation of stable warp bubbles entirely, making the concept a fascinating but highly speculative solution to interstellar travel. Despite these challenges, warp drive research has progressed in surprising ways. Some theoretical work has explored modifications to the original Alcubierre metric that dramatically reduce the amount of exotic matter required, potentially bringing the concept closer to physical plausibility. Others have considered analogues in laboratory systems, such as manipulating effective spacetime metrics using electromagnetic fields, optical metamaterials, or other analog models to better understand the physics of spacetime manipulation. While these experiments are far from creating a real warp bubble, they demonstrate that the fundamental physics can be explored and may yield insights applicable to future propulsion technologies. From a practical standpoint, warp drives remain purely speculative for now, but they represent the ultimate in theoretical interstellar propulsion. Unlike fusion rockets, solar sails, or even antimatter engines, a warp drive does not require the spacecraft to accelerate in the conventional sense, eliminating the need for continuous thrust over decades or centuries. In principle, this could allow human crews to travel to distant stars within a human lifetime, overcoming the severe limitations of time, energy, and biological endurance that plague conventional approaches. It also dramatically reduces the impact of relativity. Time dilation would be negligible within the warp bubble, meaning passengers could experience a journey lasting days or weeks, while the outside universe ages normally. Philosophically, warp drives challenge humanity to imagine the very fabric of reality as a navigable medium. They represent a vision in which the universe itself becomes a tool for exploration rather than an obstacle to be overcome, suggesting that the laws of physics may hold hidden possibilities for travel that conventional engineering cannot exploit. At the same time, they force us to confront the limits of knowledge and the enormous gap between theoretical possibility and practical implementation. Even if exotic matter and bubble stabilization remain unattainable, the concept of warp drives expands the scope of imagination, prompting scientists to consider the universe not just as a vast space to traverse, but as a dynamic, malleable structure that could one day be harnessed. In essence, warp drives encapsulate both the greatest promise and the deepest uncertainty of interstellar travel. They offer a potential method of reaching distant stars faster than light without violating local physical laws, yet they demand resources, materials, and understanding far beyond anything currently available. The concept illustrates the profound interplay between theoretical physics and human aspiration. Even as we struggle with chemical rockets, fusion engines, and robotic probes, the Alcubierre drive represents a vision of what might be possible when imagination, mathematics, and advanced technology converge. For humanity, warp drives are not just a propulsion idea. They are a symbol of our enduring desire to traverse the cosmos, to shorten the impossible distances between stars, and to challenge the very boundaries of space and time. The human problem. While physics and engineering dominate discussions of interstellar travel, the most profound obstacles may lie within the human mind and body. Sending people to the stars involves challenges not faced by robotic probes or light sails. Even if propulsion, energy, and structural issues were resolved, the biological and psychological endurance of humans over decades, centuries, or millennia remains a formidable barrier. Long-term space habitation introduces a cascade of health risks, from microgravity-induced physical degeneration to the mental strain of extreme isolation, confinement, and intergenerational societal continuity. The human problem highlights that interstellar travel is not only a technical challenge, but a deeply human one. One of the most immediate biological concerns is the effect of microgravity or artificial gravity on the human body. Prolonged exposure to weightlessness causes muscle atrophy, bone density loss, and cardiovascular deconditioning. On long interstellar journeys, these effects could become catastrophic unless continuous countermeasures, such as resistance exercise, artificial gravity, or rotation-based gravity systems, are implemented. Even with these measures, humans evolved to thrive under Earth's gravitational conditions, and life support systems must be designed to mitigate these physical declines over potentially centuries of travel. Radiation exposure is another critical challenge. Interstellar space is filled with cosmic rays, high-energy particles, and solar radiation that can penetrate spacecraft shielding and damage human DNA. Over decades or centuries, this exposure increases the risk of degenerative diseases and genetic mutations. Shielding a large crew for prolonged periods requires substantial mass, often making spacecraft heavier and more difficult to accelerate. While robotic probes can survive harsh radiation with hardened electronics, humans are far more vulnerable, and mitigating these risks without impractically massive shielding remains a central problem. Psychological and social challenges are equally formidable. Isolation, confinement, and the absence of natural social interaction can trigger profound mental health issues. On generational ships, where multiple human cohorts live and die en route to distant stars, the psychological stress of knowing that one may never see Earth again, or that one's descendants will continue the mission without choice, can be immense. Maintaining morale, social cohesion, and a stable society over centuries is unprecedented in human history. Communication delays of years with Earth remove the possibility of immediate support or guidance, placing the entire responsibility of problem-solving and governance on the crew itself. Generational ships compound these challenges further. Future generations would be born and raised entirely in an artificial environment, disconnected from natural Earth ecosystems, planetary cycles, and social structures. This raises questions of identity, cultural preservation, and education. Would successive generations retain the mission's purpose, or would societal drift occur, potentially leading to mutiny, social breakdown, or abandonment of the mission? The human problem is therefore not merely physical. It encompasses complex social, ethical, and cultural dimensions that are difficult to quantify or predict. Nutrition and health maintenance present additional hurdles. Long-duration missions require closed-loop life support systems capable of recycling air, water, and nutrients for multiple generations. Food production in confined artificial habitats poses significant engineering and biological challenges. Even small genetic defects could amplify over generations if not carefully monitored, raising the specter of long-term population viability issues. Medical care becomes another monumental concern. With centuries-long missions, the crew must possess the skills, equipment, and autonomous decision-making ability to treat a full spectrum of illnesses and injuries without hope of resupply. Cognitive and social adaptation also presents an often overlooked barrier. Humans evolved over millions of years in complex natural environments, with social structures, sensory stimuli, and challenges vastly different from a sterile, confined starship. Psychological resilience must be cultivated, but predicting how individuals and communities respond to prolonged monotony, isolation, or generational separation from Earth is nearly impossible. Long-term missions may induce cognitive decline, chronic stress, or social dysfunction unless mitigated by sophisticated environmental design, virtual reality immersion, or carefully managed community dynamics. Even if these challenges were met, the very notion of voluntarily committing to a centuries-long journey raises ethical questions. Would it be morally defensible to send individuals on a voyage whose duration exceeds their natural lifespan, knowing they may never return to Earth? For generational ships, consent becomes a multi-generational issue, as future generations would inherit a mission chosen before their birth. Balancing the drive for exploration with human rights, psychological welfare, and societal stability adds a profound layer of complexity to interstellar ambitions. In conclusion, the human problem underscores that interstellar travel is not solely an engineering or scientific challenge. It is a deeply human one. Biological limits, radiation exposure, microgravity effects, psychological stress, social cohesion, and ethical dilemmas all combine to make long-duration human missions extraordinarily difficult. Even with breakthroughs in propulsion, energy, and spacecraft design, the human mind and body impose constraints that cannot be ignored. Addressing these challenges will require not just advanced technology, but revolutionary thinking about society, biology, and human resilience. Until these problems are solved, robotic and AI-driven exploration may remain the practical bridge to the stars, carrying humanity's curiosity across interstellar distances, while our own species grapples with the profound implications of leaving the cradle of Earth. The communication delay. Even if humanity develops the technology to reach nearby star systems, one of the most profound limitations of interstellar travel is the sheer delay in communication over such vast distances. The speed of light becomes a restrictive boundary when dealing with interstellar scales. For instance, Proxima Centauri, our nearest stellar neighbor, is about 4.24 light-years away. This means that even a message traveling at light speed would take over 4 years to reach Earth, and another 4 years for a reply to return. For missions reaching stars tens or hundreds of light-years away, communication would span decades or centuries. This imposes a profound challenge for mission control, decision-making, and the psychological well-being of crews, as real-time interaction with Earth would be impossible. For robotic probes, the delay primarily affects data transmission and control. Unlike spacecraft within our solar system, which can be remotely guided with only minutes of delay, interstellar probes must operate autonomously. They cannot rely on Earth-based guidance to make split-second navigational decisions or respond to unexpected hazards. Autonomous AI systems must be sophisticated enough to handle navigation, repairs, data collection, and emergency scenarios independently, essentially making the spacecraft a self-contained explorer with near-total operational independence. Errors or unforeseen obstacles encountered by these probes would have no immediate corrective input from Earth, increasing the mission's risk substantially. For human crews, the implications of communication delay are even more serious. Imagine a starship traveling to a system 50 light-years away. A simple inquiry or request for advice from mission control would take a century for a response to return. Medical emergencies, technical malfunctions, or social disputes cannot be immediately resolved by Earth-based experts. The crew must be entirely self-sufficient, capable of solving problems, making strategic decisions, and maintaining social order without guidance. This autonomy is unprecedented in human exploration, as even the most distant space missions within our solar system can rely on a response time of hours or, at most, days. Interstellar travel forces humanity to relinquish real-time control and accept extreme operational isolation. Communication delay also impacts scientific goals. Observations collected by interstellar probes or human explorers would not be shared instantaneously with Earth. For researchers, analyzing the first signs of an exoplanet, a potentially habitable environment, or alien phenomena would require patience spanning decades or centuries. In the context of robotic missions like Breakthrough Starshot, transmitting high-resolution images or complex datasets across light years would demand exceptionally powerful transmitters, sensitive receivers, and robust error-correcting technology to ensure data integrity over the vast distances. Each transmission would be subject not only to the time delay, but also to the risk of signal degradation from cosmic interference and interstellar dust. Even within a generational ship scenario, communication delays present profound psychological and social challenges. Crews could never have direct, timely contact with family, friends, or institutions on Earth. Entire generations might be born and die without any real interaction with the planet that launched them. This separation could lead to a sense of isolation, cultural drift, or a loss of purpose over time, potentially affecting social cohesion and morale. It also raises ethical questions about responsibility and oversight. Who ensures that a centuries-long mission remains aligned with humanity's goals if the crew cannot consult or coordinate with Earth in any meaningful timeframe? Technical solutions to mitigate communication delays are limited by the immutable laws of physics. While stronger transmitters, advanced antennas, and quantum communication concepts may improve the fidelity or efficiency of interstellar messaging, no technology can surpass the universal speed limit imposed by light. Quantum entanglement, often popularly discussed as a potential faster-than-light communication method, does not allow actual information transfer instantaneously according to our current understanding of physics. Any signal intended to carry data to Earth is constrained by the distance and the finite speed at which it propagates. Even with advanced AI handling immediate decision-making, the delayed feedback loop fundamentally changes mission design. Missions must anticipate problems far in advance and incorporate redundancy, fail-safes, and adaptive systems capable of functioning independently for decades or centuries. Communication delay forces explorers to become entirely autonomous societies or technologically self-reliant probes, reshaping how humanity approaches interstellar exploration in every respect, from propulsion to life support, from scientific observation to psychological resilience. In essence, communication delay is a non-negotiable barrier that profoundly affects every aspect of interstellar missions. It is not merely a logistical inconvenience, but a fundamental constraint imposed by the structure of space-time itself. Even if propulsion challenges, energy requirements, and human biology are solved, the delay in transmitting knowledge and receiving guidance makes interstellar exploration a radical departure from anything humanity has ever undertaken. It demands autonomy, resilience, and acceptance of isolation, reinforcing the notion that interstellar travel is as much a test of human adaptability and foresight as it is a triumph of engineering and physics. The cost barrier. Interstellar travel is not only an engineering and biological challenge, it is also an economic one of unprecedented scale. While robotic probes, fusion engines, or even speculative technologies like warp drives and antimatter propulsion may offer the possibility of reaching other star systems, the financial and material cost of such missions presents a barrier as imposing as the distances themselves. The sheer magnitude of the resources required is difficult to conceptualize, spanning entire national economies, decades of technological development, and materials whose availability may be limited or entirely theoretical. Any realistic assessment of interstellar travel must grapple with this economic dimension, recognizing that cost could determine whether such missions remain speculative dreams or become concrete objectives. To begin, consider current space missions as a baseline. The James Webb Space Telescope, a marvel of modern engineering, cost approximately $10 billion to design, construct, and launch. Robotic missions to Mars, such as the Perseverance rover, cost around $2.5 billion. These projects operate entirely within our solar system, over distances measured in millions or billions of kilometers, yet they already demand international collaboration, cutting-edge technology, and massive investments. Interstellar missions, by contrast, would operate on distances thousands of times greater, require propulsion systems far beyond current capabilities, and involve long-duration operation in deep space. Extrapolating costs from solar system missions, even a modest robotic interstellar probe could easily require tens of billions, if not hundreds of billions of dollars just to construct, launch, and operate. For crewed missions, the cost multiplies dramatically due to life support, radiation shielding, habitat construction, and the logistics of sustaining human life over decades or centuries. Fusion propulsion, for example, demands enormous upfront investment. Developing a functioning fusion reactor capable of producing continuous thrust in space would require decades of research and experimental testing, extensive materials development, and unprecedented precision in engineering. Current fusion experiments on Earth, like ITER, cost upwards of $20 billion without yet achieving net positive energy. Scaling this technology to a spacecraft capable of reaching even a fraction of light speed introduces additional costs for structural materials, heat management systems, radiation shielding, and autonomous operation. Launching such a massive spacecraft, potentially thousands of tons, into orbit or beyond, would itself require multiple heavy-lift rockets or entirely new methods of space construction, each adding billions more to the total budget. Antimatter propulsion, while theoretically incredibly efficient, is economically prohibitive with current technology. Producing even a milligram of antimatter requires energy equivalent to millions of dollars and years of operation at a particle accelerator. For a mission that might require grams or kilograms of antimatter to reach relativistic speeds, the cost would exceed the GDP of most nations many times over. Storage and containment systems for antimatter add further layers of expense and technical complexity. Even optimistic estimates suggest that antimatter propulsion, though physically conceivable, remains economically unfeasible for the foreseeable future. Generational ships and cryogenic human missions exacerbate the cost problem further. The creation of a self-sufficient spacecraft capable of sustaining hundreds or thousands of people for decades or centuries involves life support systems orders of magnitude more complex than anything developed for the International Space Station. Closed-loop ecosystems, artificial gravity systems, medical infrastructure, food production, psychological support, and redundant engineering systems all contribute to astronomical costs. Constructing, testing, and maintaining these systems over centuries or even decades requires sustained funding, will, and industrial capacity, resources that few nations could commit continuously. The cost is not just financial, but also material, encompassing vast quantities of metals, energy, and rare isotopes, some of which may need to be harvested from off-world sources, such as helium-3 from gas giants or rare metals from asteroids. Even smaller-scale interstellar concepts, like the Breakthrough Starshot initiative, underscore the financial barrier. This project proposes sending gram-scale robotic probes to Alpha Centauri at a fraction of light speed using powerful ground-based lasers to propel light sails. While the probes themselves are tiny, the infrastructure needed, laser arrays, precision optics, power generation, and coordination across decades, requires investments in the billions. Scaling up from these small probes to human-capable ships multiplies costs by orders of magnitude, highlighting the enormous disparity between current technological capability and the economic requirements for meaningful human interstellar exploration. Additionally, interstellar missions impose ongoing operational costs. Maintaining communications across light years, ensuring the reliability of autonomous systems over decades or centuries, and monitoring long-duration missions would require dedicated infrastructure, personnel, and contingency planning. Funding must be continuous over the mission's entire duration, which could span multiple human generations. Economic instability over decades or centuries could jeopardize even the most ambitious plans, making sustained international or interplanetary collaboration essential. This long-term commitment adds a further layer of complexity. Interstellar exploration is not just a technological investment, but a societal one, requiring alignment of economic priorities across nations, generations, and institutions. The cost barrier also raises questions about opportunity cost. Resources dedicated to interstellar missions are vast and could potentially address urgent needs on Earth, such as climate change mitigation, poverty alleviation, or global infrastructure development. Philosophers and economists alike must weigh the value of investing billions or trillions into projects that may take centuries to yield tangible results versus applying these resources to immediate human welfare. This tension highlights that interstellar travel is not purely a technical or scientific problem. It is also an economic and ethical challenge, forcing humanity to prioritize its goals in ways never previously required. In conclusion, the cost barrier is among the most formidable obstacles to interstellar travel. Beyond the immense distances, energy requirements, and technological hurdles, the financial and material investment needed for even the first interstellar missions is staggering. Robotic probes, fusion engines, antimatter propulsion, and generational ships all demand resources on a scale far exceeding anything humanity has previously attempted. Without breakthroughs that dramatically reduce the energy, material, or construction requirements, interstellar exploration remains not only a technological challenge, but a societal and economic one. Overcoming this barrier requires more than ingenuity. It requires unprecedented collaboration, long-term planning, and a willingness to commit the resources of entire nations and generations to a single audacious goal: reaching the stars. The first step: interstellar probes. When we consider humanity's first ventures into the vastness of interstellar space, the reality is that these will almost certainly be robotic, not human. The immense distances, prohibitive energy requirements, life support challenges, and psychological and social constraints all combine to make human travel a distant goal. Robotic interstellar probes, by contrast, are comparatively feasible within our current technological and economic framework. They do not require food, water, or oxygen, are unaffected by radiation in the same way humans are, and can survive conditions that would be fatal to any human crew. These unmanned emissaries serve as both pioneers and testbeds, pushing the boundaries of knowledge while establishing the practical foundations for eventual human interstellar exploration. Robotic probes have distinct advantages in size, mass, and cost. Unlike human missions, which must include massive life support systems, radiation shielding, propulsion fuel, and provisions for decades or even centuries, robotic probes can be extremely lightweight. Consider the concept of nanocraft as envisioned by the Breakthrough Starshot initiative. These probes, weighing only grams, would carry cameras, sensors, and communication devices, and could be accelerated to up to 20% the speed of light by Earth-based laser arrays. This approach drastically reduces the material and energy requirements, making interstellar travel feasible within a scale that humanity can reasonably achieve in the near future. A robotic probe does not need the mass or infrastructure required to sustain human life, eliminating the need for thousands of tons of shielding, food, water, and medical facilities. The simplicity of these small craft makes them much more achievable than crewed missions, while still allowing them to gather critical scientific data. Autonomy is a defining feature of interstellar probes. Unlike missions within our solar system, where communication delays are measured in minutes or hours, interstellar probes face delays spanning years. For example, a probe sent to Alpha Centauri would experience a communication lag of over 4 years each way, making real-time guidance from Earth impossible. Consequently, these probes must be highly autonomous, capable of making complex navigational decisions, detecting and responding to hazards, repairing minor damage, and prioritizing scientific objectives independently. Artificial intelligence and sophisticated programming are essential, essentially transforming each probe into a self-sufficient explorer capable of operating across decades or centuries without human intervention. The development of such autonomous systems is not merely a convenience, it is a necessity for survival and mission success in the vast, unforgiving interstellar medium. Durability and resilience are also critical advantages of robotic systems. Interstellar space is a hostile environment, filled with cosmic radiation, micrometeoroids, extreme temperatures, and sparse interstellar gas that can erode materials over time. While humans require substantial shielding to survive radiation exposure, robotic electronics can be hardened, redundant systems can compensate for failure, and miniaturized spacecraft can tolerate conditions that would be catastrophic for humans. In this way, robotic probes act as both a reconnaissance tool and a risk mitigation strategy. They can encounter and survive hazards that would endanger human missions, providing critical information that will guide the design and construction of eventual crewed starships. The cost efficiency of robotic probes cannot be overstated. Launching a human interstellar mission could require trillions of dollars in infrastructure, propulsion, life support, and materials. In contrast, small robotic probes cost orders of magnitude less, making them achievable within national or international space program budgets. Initiatives like Breakthrough Starshot, while ambitious, remain economically plausible because of the miniaturization of components and reliance on external propulsion via lasers, rather than carrying massive fuel loads on board. The financial accessibility of robotic probes makes them a pragmatic choice, allowing humanity to begin interstellar exploration without waiting for technologies like fusion or antimatter propulsion to mature to a human-viable scale. Robotic probes also offer scalability. Multiple probes can be sent simultaneously to the same target or to multiple star systems, forming a distributed network of explorers. Swarm strategies, where dozens or hundreds of tiny craft operate collectively, enhance mission resilience and scientific return. If one probe fails, others continue the mission, and the collective data can provide a richer and more comprehensive understanding of the target system. This approach is fundamentally different from human missions, which must maintain the survival and functionality of every crew member, making redundancy far more complex and costly. With robotic probes, the risks are distributed across the swarm, allowing bold, innovative experimentation without endangering human life. Scientific output is another compelling reason to prioritize robotic interstellar probes. Even small probes equipped with modern instruments can collect unprecedented data about nearby stars, planetary systems, and the interstellar medium. They can analyze cosmic dust, magnetic fields, radiation levels, and even search for signs of habitable planets or biosignatures in exoplanetary atmospheres. This information is invaluable for both scientific knowledge and the preparation of future human missions. Robotic probes effectively act as scouts, reducing uncertainty and enabling humans to make informed decisions when the time comes to commit to crewed missions. In addition, the longevity and durability of robotic craft mean they can continue returning data for decades, far beyond what any human crew could sustain. Beyond practicality, robotic interstellar missions are a natural extension of humanity's historical approach to exploration. Throughout history, humans have often sent proxies into dangerous or distant environments before venturing personally. From unmanned reconnaissance vehicles exploring remote landscapes to robotic probes traversing the solar system, technology has consistently allowed us to extend our reach while minimizing risk. Robotic interstellar probes are the logical next step in this progression, extending our presence to other star systems while preparing the ground for eventual human expansion. In addition, robotic missions can test and refine technologies critical for future human travel. They allow us to evaluate propulsion systems, radiation shielding, long-distance communication, and autonomous decision-making in real interstellar conditions. Lessons learned from robotic probes will inform spacecraft design, mission planning, and risk assessment for generations. In this sense, the first robotic probes are not merely a stepping stone. They are an essential bridge that enables humanity to learn, adapt, and evolve towards safe, sustainable, human interstellar travel. In conclusion, robotic interstellar probes are the most feasible, practical, and scientifically valuable first step into the stars. They circumvent the immense challenges posed by human biology, life support, and psychological endurance while remaining economically achievable and technologically attainable in the near future. These probes will serve as humanity's first emissaries to other star systems, gathering data, testing technologies, and reducing risk for future human explorers. While the dream of humans traveling to the stars captures our imagination, it is these robotic pioneers that will carry humanity's curiosity across light years, mapping the cosmos and preparing the foundation for the eventual, long-awaited journey of people themselves. In many ways, the first true interstellar journey has already begun, not with humans stepping onto distant worlds, but with small, intelligent machines venturing into the cosmic unknown, paving the way for our species to follow when the time and technology finally allow. Philosophical question. As humanity contemplates the immense challenges, costs, and possibilities of interstellar travel, a critical question emerges. Is it even necessary? Beyond the physics, engineering, biology, and economics, there is a deeper, more philosophical consideration about the purpose and value of venturing to the stars. While the idea of exploring other star systems captures the imagination and embodies humanity's innate curiosity, one must ask whether the monumental effort required to leave our solar system is justified, especially when pressing challenges on Earth remain unresolved. The philosophical question forces us to consider the ethics, priorities, and ultimate goals of our species. Should we risk enormous resources and generations of effort to journey to other stars? Or should we focus our ingenuity and ambition on making our home planet sustainable, habitable, and resilient for future generations? At the heart of this debate is the recognition that Earth, despite its vulnerabilities, is uniquely suited to sustain life as we know it. It provides an intricate, balanced ecosystem, abundant water, breathable atmosphere, and the natural cycles that have allowed life to flourish for billions of years. In contrast, even the most promising exoplanets identified by astronomers are unlikely to be immediately habitable. The distances involved mean that colonizing another star system would require not only transporting humans across light years, but also terraforming or adapting to worlds that may be harsh, barren, or radiation-baked. The logistical, technological, and biological challenges of making such planets hospitable are monumental and may exceed the capabilities of humanity for centuries, if not millennia. From this perspective, the argument emerges that investing resources in sustaining Earth may yield a greater return in human survival and quality of life than attempting to escape to distant stars. Sustainability on Earth is an increasingly urgent concern. Climate change, biodiversity loss, resource depletion, and environmental degradation threaten the very systems that support human civilization. Even if interstellar travel becomes possible, leaving Earth in a degraded state does not solve the problem. It merely shifts the burden to a distant and untested environment. Philosophically, one could argue that true human advancement lies not in leaving our problems behind, but in mastering them, creating a sustainable and resilient civilization capable of enduring the long term. Developing clean energy, restoring ecosystems, managing population growth, and ensuring equitable access to resources are challenges that directly affect billions of people today. Prioritizing these objectives addresses the survival and flourishing of humanity within the only home we currently know can reliably support us. Interstellar travel while a remarkable goal, also raises ethical considerations about resource allocation. A single crewed mission to a nearby star system could cost trillions of dollars and decades or centuries of sustained effort. Those resources could instead fund global initiatives to end poverty, improve healthcare, develop sustainable agriculture, or mitigate climate change. The philosophical dilemma is one of opportunity cost. Pursuing interstellar exploration is not a neutral choice. It diverts intellectual, financial, and industrial resources from pressing global issues. Is it morally defensible to commit generations of effort to a project that may not guarantee survival or meaningful benefit for humanity, when those same resources could directly enhance life on Earth? Yet, proponents of interstellar exploration argue that the endeavor is not only about survival, but also about potential long-term species resilience. Earth faces existential threats ranging from asteroid impacts to supervolcanic eruptions or global nuclear conflict. While these events are statistically rare, their consequences could be catastrophic, potentially ending human civilization. From this perspective, interstellar colonization functions as a cosmic insurance policy. Spreading humanity across multiple star systems could theoretically ensure the continuation of our species, safeguarding against extinction events that might obliterate a civilization confined to a single planet. Philosophically, this raises the tension between immediate ethical responsibilities to present generations and long-term existential considerations for the species. Interstellar ambitions also reflect humanity's innate curiosity and drive for exploration, which has historically been a source of cultural, technological, and philosophical growth. Venturing into unknown territory challenges the limits of knowledge, spurs innovation, and cultivates a sense of purpose beyond the immediate concerns of survival. The urge to explore the cosmos may be viewed as an extension of the same impulse that led humans to sail across oceans, map continents, and traverse harsh landscapes throughout history. Philosophically, one could argue that stifling this drive risks limiting human potential, creativity, and cultural evolution. Exploration, whether interstellar or planetary, satisfies a deep-seated need for discovery, understanding, and the expansion of consciousness. However, this philosophical imperative must be balanced against practical constraints and moral obligations. There is a risk that interstellar dreams could become a form of escapism, attempting to leave behind unsolved societal, environmental, or ethical challenges on Earth rather than addressing them. If humanity attempts to colonize other stars while neglecting the stewardship of its home planet, we may repeat the mistakes of unsustainable resource exploitation and environmental degradation on a cosmic scale. This perspective emphasizes that interstellar travel should not be pursued as an alternative to solving Earth's problems, but rather as a complement to them, an aspirational goal integrated with responsible planetary management. Another dimension of the philosophical question is cultural and existential identity. Our species' identity is deeply tied to Earth, not just as a physical home, but as a cradle of life, culture, and history. Leaving Earth entirely, or even establishing permanent off-world colonies, raises profound questions about the meaning of home, the continuity of culture, and the psychological impact on future generations who may never experience the natural world as we know it. Philosophically, interstellar travel is not merely a technological undertaking, but a transformation of what it means to be human. Our concepts of family, society, and belonging are challenged when the stars themselves become our destination. Some philosophers argue that interstellar travel may be necessary not purely for survival, but for the evolution of consciousness and civilization. Expanding humanity into the cosmos could foster new forms of governance, society, and culture that transcend planetary limitations. It may catalyze philosophical growth by confronting humans with existential scale, cosmic timeframes, and the mysteries of life in the universe. In this sense, interstellar exploration is not merely a physical journey, but an intellectual and cultural imperative. extending human inquiry and aspiration to a universal stage. Ultimately, the philosophical question of interstellar travel is a balancing act between aspiration and responsibility. On one hand, exploring the stars could ensure species survival, expand knowledge, and fulfill a fundamental human drive for discovery. On the other hand, the immediate moral, environmental, and social obligations on Earth are profound, requiring concentrated attention, resources, and ingenuity. Philosophically, the question challenges humanity to prioritize, weigh long-term species-level imperatives against the welfare of present generations, and define what necessity truly means. Is interstellar travel a crucial safeguard and inevitable destiny, or is it a visionary distraction from the urgent task of caring for our only proven home in the cosmos? There may be a synthesis between these perspectives. Responsible interstellar exploration need not conflict with sustainable stewardship of Earth. In fact, the technologies, knowledge, and societal cooperation required for interstellar travel could accelerate progress in environmental sustainability, resource management, and global governance. For example, advances in energy generation, closed-loop life support systems, and resource-efficient technologies developed for space travel can be applied to Earth's challenges. Similarly, the cooperative frameworks required for multi-decade interstellar missions could foster global unity and long-term thinking, cultivating a planetary perspective essential for addressing climate change and ecological degradation. In this way, interstellar exploration and Earth sustainability are not mutually exclusive, but can be mutually reinforcing goals. In conclusion, the philosophical question of interstellar travel forces humanity to confront its values, priorities, and ethical responsibilities. It asks whether the stars are a necessary destination, or whether our first duty lies in protecting and sustaining Earth. The answer may not be absolute, but rather contextual. Interstellar travel may be essential for long-term species survival and the expansion of human knowledge, yet it cannot justify neglecting the pressing challenges of our home planet. By balancing ambition with responsibility, curiosity with ethical stewardship, humanity can pursue the cosmos without abandoning the very cradle of life that made such exploration possible. Philosophically, the journey to the stars may be both a literal and metaphorical test, a measure of whether our species can rise to cosmic responsibility while honoring the fragile, precious world from which we began. Closing, as we reflect on the staggering challenges, breathtaking possibilities, and profound philosophical questions surrounding interstellar travel, one truth becomes clear. The road to the stars is as much a question of human imagination as it is of technology or physics. Even if it takes centuries or millennia to reach our nearest stellar neighbors, the idea that humanity could one day traverse the void between stars is both humbling and exhilarating. From the earliest lunar landings to robotic probes skimming the edge of our solar system, each achievement has expanded the boundaries of what we believe is possible. Yet interstellar travel represents a scale and scope beyond anything humanity has attempted before, a journey that will stretch not only our technology, but our patience, creativity, and endurance across generations. The universe beckons with its mysteries, each star a potential beacon of discovery, each exoplanet a canvas for understanding life beyond Earth. Even if the nearest stars are light years away, their distances invite reflection on our place in the cosmos, reminding us that we are simultaneously infinitesimal and extraordinary. The road to the stars is not just a technological challenge, it is a philosophical and existential one. It forces humanity to ask questions about identity, responsibility, and ambition. Are we content to remain bound to our sun, confined to a single planetary cradle? Or is our destiny to reach beyond, to stretch across the cosmos, and perhaps, in doing so, redefine what it means to be human? As robotic probes carry our first messages across light years, as theoretical concepts like warp drives and wormholes tantalize the imagination, And as generational ships or cryogenic sleep technology linger in the realm of possibility, humanity faces a choice: to remain within the known safety of our solar system, or to embrace the unknown. Each step, each probe, each experiment is a testament to curiosity, courage, and the ceaseless drive to explore. Even the communication delays, the energy requirements, the psychological and social barriers, and the economic costs cannot diminish the allure of the stars. They are challenges, yes, but they are also invitations to push, to learn, to imagine, and to transcend our planetary limits. Ultimately, the question remains open, and perhaps deliberately so. Even if centuries pass before a human sets foot on another world, the spark of curiosity and exploration that drives us today ensures that the idea of interstellar travel will never fade. It is a challenge that may take generations to meet, a dream that may outlast our own lifetimes, and a journey that reminds us that humanity is defined by its willingness to look beyond the horizon. The road to the stars is not a certainty, but it is a possibility woven into our nature, beckoning us to contemplate, innovate, and aspire. The universe waits, vast, mysterious, and indifferent, yet filled with opportunity for those willing to reach across the cosmic gulf. So, as you watch the probes leaving the solar system, as theories of warp drives and light sails ignite the imagination, and as the philosophical questions linger about our place in the cosmos, one thought remains: even if it takes centuries, even if obstacles seem insurmountable, the stars are out there, and the road to them may very well be humanity's ultimate fate. Will we remain bound to the comforting glow of our sun, or will we heed the call of the cosmos, venturing into the unknown and claiming our place among the stars? The answer, for now, lies in the future, waiting for those with the vision, courage, and persistence to see it through. The journey may be long, the challenges monumental, and the obstacles nearly unimaginable. Yet the very act of contemplating interstellar travel elevates humanity's aspirations. We are, after all, a species defined by exploration, by curiosity, and by the relentless pursuit of knowledge. The stars are no longer just distant points of light. They are a mirror reflecting our potential, our daring, and the boundless scope of our imagination. And perhaps one day, they will also be the destinations that define our destiny. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.